In the annals of physics, few theories have evoked such contradictory feelings, simultaneously inspiring deep devotion and fierce rejection. Its journey has indeed been a thrilling roller coaster, marked by dizzying ascents and equally rapid descents. Scientists who dedicated their lives to it are rightly regarded as true scientific adventurers. Many, facing immense difficulties, eventually had to retreat, yet some remained steadfastly loyal to its principles even during periods of widespread condemnation and skepticism. Should string theory ever achieve the ultimate, all-encompassing form its creators dream of, that event would undoubtedly make for a Hollywood blockbuster. For now, the story of this grand scientific odyssey is far from over, and string theory has not yet emerged as a fully formed and complete body of knowledge. It's no surprise that many call it speculative, and for good reason. None of its predictions have yet received experimental confirmation. Furthermore, some believe such confirmation is fundamentally impossible. However, despite decades of unsuccessful attempts to unify the fundamental principles of quantum mechanics and general relativity, string theorists have advanced further than anyone else in this direction. Can this concept reveal the universe's deepest laws? That is a question keeping the entire scientific community on edge. The quest for a unified theory in physics has been a central idea, inspiring brilliant minds for centuries. Every physicist dreamed of creating a single, comprehensive theory capable of explaining every phenomenon observed in the universe. Isaac Newton achieved a breakthrough by unifying celestial and terrestrial mechanics, demonstrating that the same laws governing the motion of the moon and other celestial bodies also apply to objects on Earth. 2 centuries later, in the 19th century, James Clerk Maxwell took another grand step, mathematically unifying electricity and magnetism and showing them to be merely two different manifestations of a single fundamental force of nature. In the early 20th century, Albert Einstein took up the mantle. His special theory of relativity, published in 1905, unified space and time into a single four-dimensional spacetime. A decade later, in 1915, he expanded his theory, offering a description of gravity that remains the most accurate approximation of the real universe to this day. However, this triumphant march of science towards unification encountered an unexpected yet significant obstacle. In the 1920s, eminent scientists such as Max Planck, Niels Bohr, Werner Heisenberg, and others made breakthroughs in studying the microworld, revealing its quantum nature. All these new quantum laws proved exceptionally successful in predicting the behavior of atoms and the smallest fundamental particles, but they entirely bypassed gravity. For several decades now, the struggle for unification has been unable to overcome this barrier. General relativity and quantum mechanics seem incapable of forming a robust and harmonious union. So what about string theory? Its journey, in fact, did not begin as an ambitious project to create a unified theory of everything. It was far more modest. In the 1960s, physicists faced significant difficulties in trying to understand the strong interaction, one of the four fundamental interactions, which, among other things, holds protons and neutrons together within atomic nuclei. By then, scientists already had an extremely successful theory describing another interaction, electromagnetism. Quantum electrodynamics, or QED, was a quantum field theory that, to this day, is considered an elegant and effective way to explain electromagnetism. It successfully combined the principles of special relativity and quantum mechanics. It was therefore natural for physicists to try applying the same principles to explain the strong interaction, but they encountered certain problems. Firstly, the strong interaction, as its name suggests, proved to be significantly stronger than the electromagnetic one. Secondly, during experiments, physicists began discovering an excessively large number of different particles associated with it. In scattering experiments, where particles collided and transformed into others or scattered at various angles, dozens, even hundreds, of new particles emerged, now known as hadrons. It turned out that mathematically describing each of them with a separate quantum field was extremely complex and cumbersome. Naturally, physicists had to seek a completely different approach. Today, scientists know how to solve this problem, and we have quantum chromodynamics to describe the strong interaction. But before its advent, various alternative approaches were proposed. This is where Gabriele Veneziano enters our story. He was one of those who sought to find a simple mathematical model capable of describing the strong interaction. Instead of meticulously describing the interaction of all fields, he decided to take a bottom-up approach, using experimental data to find a general mathematical expression that would describe them. After 9 months of intense work with 3 colleagues, he finally managed to derive the necessary function, which perfectly described the strong interaction. A curious twist in this story was that, while flipping through a textbook of various mathematical functions, Veneziano suddenly stumbled upon his own expression. It turned out that the great mathematician Leonhard Euler had recorded it back in the 18th century. But this historical quirk is not what interests us. In 1970, 3 physicists, including Leonard Susskind, whom you might know, took notice of Veneziano's work and observed something intriguing in his function. First, we must remember that the best model of particle physics we have is the Standard Model. Essentially, it describes fundamental forces, such as electromagnetism or nuclear forces, through the exchange of virtual bosons between matter particles. For instance, 2 electrons repel each other due to their identical negative electric charges, and the Standard Model tells us that this repulsion occurs via virtual photons exchanged between the pair of electrons. Importantly, in this model, elementary particles are described as point-like entities, having no measurable size. In other words, they are ordinary, tiny points without internal structure or dimensions. But Susskind and his colleagues showed that the very same Veneziano formulation could be derived from a completely different assumption, that elementary particles are not points. In fact, they could be viewed as string-like objects, tiny threads of energy resembling string fibers. And this discovery forever changed the course of theoretical physics, paving the way for the boldest hypotheses about the nature of reality. The fundamental concept, fortunately for researchers and curious minds, turns out to be quite straightforward. If one imagines any particle responsible for carrying fundamental forces, such as a photon, which is the quantum of electromagnetic interaction, and views it through an imaginary, yet currently unrealizable, super-powerful microscope, it becomes evident that this particle is nothing more than an incredibly miniature, vibrating string. In some configurations, this string can be open, being a one-dimensional entity with 2 clearly defined endpoints. In other circumstances, it closes into a loop, resembling a vibrating ring. The diversity of elementary particles observed in nature is solely due to their fundamental strings being capable of various types of vibrations. Each unique mode of vibration of such a string gives rise to a distinct particle possessing a specific set of properties. Thus, it is these strings, and not any other objects, that serve as the true elementary, indivisible constituents of the universe. The question of their internal structure becomes meaningless. They are, by themselves, the basic building blocks of all matter and energy. It is important to emphasize that vibrational movements are not the only characteristic of strings. In scientific literature, the fact of their active interaction with each other is sometimes overlooked. These threads can merge, split, and reflect upon collision. For example, when 2 strings combine, a new string emerges, which in a macroscopic sense signifies the birth of a new particle. Conversely, when they decay, 2 different entities are formed. It is this dynamic picture that corresponds to the complex physical phenomena researchers record during experiments at modern particle accelerators. This aspect is one of the key features of string theory, as it does not merely describe the particles themselves but also organically incorporates the concept of interaction, which stems directly from the internal geometry of these fundamental entities. Undeniably, such an interpretation of the universe proved highly intriguing and, at the time, generated considerable interest within the scientific community. However, despite its mathematical elegance and appeal, the early version of this theory also had significant drawbacks. Firstly, this concept exclusively encompassed bosons, particles responsible for mediating fundamental interactions. Fermions, from which all familiar matter is composed, remained outside its description. It is for this reason that the first iteration of string theory is commonly referred to as bosonic string theory. Secondly, when physicists attempted to harmonize this theory with special relativity and the principles of quantum mechanics, certain anomalies inevitably arose in their calculations. To eliminate these inconsistencies, scientists had to introduce additional spatial dimensions into the theoretical model, with their number reaching as many as 22. Thus, according to string theory at that time, our universe possesses not the 4 dimensions familiar to human perception, but 26, most of which evidently remain invisible to us. This implies that strings vibrate not only along the familiar axes, back and forth, up and down, or left and right, but also in a multitude of other dimensions, without which the theory simply ceases to function. This feature seemed quite exotic, but string theorists later attempted to transform it into a more constructive direction. At that time, they also had to contend with the fact that string theory predicted the existence of a special type of boson whose mass was described not by a real number, but by an imaginary one. These hypothetical particles, named tachyons, were supposed to travel faster than the speed of light in a vacuum, and they could never slow down to sublight speeds. Such a mathematical artifact, as one can easily guess, was highly undesirable. Ultimately, the first version of string theory ceased to exist not even for this reason. Gradually, more precise data on the strong interaction accumulated, and they stopped aligning with string theory's predictions. Since experiment has always been and continues to be the ultimate arbiter in science, strings very quickly lost their former popularity, and their final demise was marked by the advent of quantum chromodynamics, a theory that described the strong interaction significantly better. Quantum chromodynamics, QCD, introduced the concept of quarks, which make up protons and neutrons, into scientific discourse, and the interaction between them, according to this theory, was mediated by other particles called gluons. To this day, quantum chromodynamics remains the universally accepted theory of the strong nuclear force. Thus, early string theory became obsolete. The vast majority of physicists turned away from it, with the exception of a small group of dedicated proponents. Among the few but extremely determined adherents of string theory were John Schwarz from Caltech, as well as French physicists André Neveu and Joël Scherk. Through their combined efforts, they attempted to take a fresh look at the concept of strings. These theorists realized that continuing to view string theory as solely a theory of the strong interaction made no sense. Instead, its original purpose needed to be changed. Besides bosons, particles that mediate interactions, it was necessary to include fermions, the elementary particles from which all observable matter is actually built. However, the question arose as to how this could be achieved, as fermions and bosons possess fundamentally different properties and obey different statistics in quantum mechanics. Thus, making them dance in unison was a highly non-trivial task. In the early 1970s, Schwarz and Neveu discovered an elegant solution. They turned to the principle of supersymmetry, a name that, admittedly, sounds impressive, which is not surprising given the presence of the word super. This is another purely theoretical construct that postulates that in nature, every boson particle has its supersymmetric fermion partner, and vice versa. For example, a photon, which is a boson, has its superpartner, a photino, which is a fermion. Similarly, an electron, undoubtedly a fermion, has a partner, selectron, which is a boson. A quark has a squark, a neutrino has a neutrino, and so on. Indeed, this field abounds with many unusual names, such as glino, bino, xeno, higgsino, and even wino. The key idea to grasp is that the principle of supersymmetry allows for the mathematical integration of fermionic string vibrations into the theory. In other words, new modes of string vibration now endowed particles with fermionic properties. The theory finally gained the ability to describe quarks, electrons, muons, and neutrinos, essentially every known elementary particle in nature. The differences between them, particularly in mass and charge, arise solely from the dissimilar vibrations of their internal strings. This entire vast list of diverse particles discovered over a century of experimental research was transformed into harmonious notes, composing nature's grand symphony. Thus, the previous string theory underwent significant changes and was reborn in a new capacity, receiving the name superstring theory. This transformation was made possible by the introduction of the principle of supersymmetry. Notably, this development led to not one, but 5 different string theories, each incorporating fermions, possessing supersymmetry, and being in full agreement with the principles of quantum theory. An important achievement was that the new mathematical framework naturally eliminated tachyons, particles that previously represented, to put it mildly, a highly undesirable artifact of string models. Furthermore, the superstring concept allowed for reducing the required number of space-time dimensions to 10. Now, to our familiar 4 dimensions, length, width, height, and time, only 6 invisible dimensions were added, significantly fewer than the previous 22. However, there was yet another aspect that was perceived as truly revolutionary. During calculations concerning the string vibration spectrum, a special particle invariably appeared. This particle, though undetectable by any accelerator experiment, had long been anticipated by physicists. We are talking about the graviton, a hypothetical particle that was supposed to be responsible for the gravitational interaction. Its natural emergence in string theory was a real shock to John Schwarz and his colleagues. After all, a theory originally intended to describe the strong interaction unexpectedly incorporated gravity. Previously, physicists had unsuccessfully tried to integrate the graviton into the standard model, but every such attempt led to the breakdown of the entire mathematical structure. Here, its existence organically flowed from string theory. Could this merely be a coincidence? Therefore, the next assumption put forward by Schwarz and his collaborators proved highly logical, albeit extremely bold. What if string theory was the very physical theory that had been sought for decades? What if strings were the true theory of quantum gravity, a kind of theory of everything? How, in the researchers' view, did the scientific community react to this seemingly breakthrough discovery? Exactly as predicted. In fact, the vast majority of scientists ignored it. String theory had already failed in its initial incarnation when it claimed to describe the strong interaction. With such a reputation, it was extremely difficult to believe in it a second time, especially when it concerned solving a far more complex and fundamental problem. That was one reason. Secondly, the theory itself was still relatively raw at the time, if one can put it that way. Its mathematical framework contained infinities, which, as is known, always indicate serious problems, as well as various anomalies and difficulties with symmetries. Simply put, at certain key points, the mathematics broke down, and it was unclear whether a consistent and coherent theory of quantum gravity could even be built from all these elements. Moreover, the principle of supersymmetry itself was another controversial concept, as no supersymmetric particle with any exotic name had ever been detected. Perhaps, like the strings themselves, they are hidden at energy levels orders of magnitude beyond what is accessible in modern accelerators. And finally, the extra dimensions. They were still perceived by many physicists as evidence of the theory's imperfection, or even artificiality. Due to all these unresolved issues, string theory was once again abandoned, and this time the number of skeptics grew significantly. John Schwarz, recalling that period, noted, "Yes, it's strange, but the community didn't react much to our papers and lectures. In general, we were respected, and we never had trouble publishing our papers, but there wasn't much interest in the idea. We were proposing a quantum theory of gravity, but at that time, physicists working on quantum theory weren't interested in gravity, and physicists working on gravity weren't interested in quantum theory. In fact, until the mid-1980s, only a handful of people were working on superstring theory, consistently including Schwarz and his new colleague Michael Green, then a theoretical physicist at Queen Mary College, University of London. Schwarz and Green met in the summer of 1979 in the CERN cafeteria. It was thanks to their subsequent persistent efforts that string theory gained the significant popularity it enjoys today. In 1984, they published a landmark paper titled Anomaly Cancellations in Supersymmetric Gauge Theories and Superstring Theory. The anomaly cancellations, the authors wrote about, meant they had successfully eliminated infinities in calculations and other serious mathematical difficulties. Simply put, string theory ceased to contain internal mathematical contradictions, which its theorists hailed as nothing short of a grand breakthrough. And it truly was. Finally, the achieved mathematical consistency attracted the close attention of the scientific community. Numerous graduate students, and even experienced faculty members were literally captivated by the potential of strings to become the all-encompassing theory physicists had sought for decades. Discussions about strings unfolded both in university hallways and in crowded auditoriums where entire seminars were dedicated to the theory. It seemed a new era in physics was just around the corner, within arm's reach. However, the main and most fundamental question remained unanswered. Is string theory truly an adequate and real description of our universe? The way to answer it is known to every scientist. It is, unequivocally, experiment. But the elegant yet devilishly complex mathematics of strings severely limited their size, which turned out to be 1,000,000 billion times smaller than what can be probed even with the most powerful modern accelerators. Thus, strings easily evade direct detection, at least until someone builds a collider the size of our Milky Way galaxy. Among other things, until recently a solution for the problem of extra dimensions was needed, as the concept of a universe containing more spatial dimensions than those familiar to us did not find widespread approval. In an attempt to resolve this difficulty, string theorists turned to an idea first articulated in the 1920s. Physicists then realized that two different types of spatial dimensions could potentially exist in nature. The first type consists of vast and extended dimensions, in which humanity resides and which it perceives directly. The second type consists of dimensions that are too miniature and compact to be noticed. As an illustration of this concept, consider an ordinary rope, for example, a cable. If viewed from afar, it appears as a one-dimensional object, a simple line possessing only length. However, upon approaching and looking more closely, it becomes evident that the cable actually possesses volume. It ceases to be one-dimensional and turns out to be a three-dimensional object with its own circumference. If one looks even more closely, it can be observed that the cable consists of several thinner ropes, tightly interwoven. These thin ropes represent analogues of additional dimensions that might simply go unnoticed if the object is not observed at the correct scale. Thus, the question arises, why shouldn't the universe have not only the large dimensions in which we live, but also additional, so compact, dimensions that we are simply unable to detect even with the most powerful observational tools? One of the most influential theoretical physicists of that time, Edward Witten, showed deep interest in strings and the concept of compact dimensions. In 1985, Witten, in collaboration with three colleagues, published a paper in which they demonstrated that extra dimensions were not a flaw in string theory but, on the contrary, represented an advantage. The compactness of the extra dimensions potentially opened up a possibility for experimental verification of the theory. The main idea is that strings vibrate not only in the three large dimensions but also within these tiny extra ones. Consequently, their geometry takes on a certain significance for the ways strings vibrate. In fact, physicists came to understand that the shape of the extra dimensions does not merely influence, it determines how strings vibrate. Now, it should be recalled that vibration modes determine the types of particles that exist in the universe, i.e., their masses, spins, interaction types, and so on. From this, it logically follows that the geometric shape of the extra dimensions also determines what types of particles can exist in a given universe at all. Just as the shape and weaving method of ropes in a cable provide an accurate prediction of its structure, so too can the shape of extra dimensions provide a prediction about observable particles. Thus, physicists gained hope that string theory's predictions might be discovered in the real universe. For this, it was only necessary to understand the geometric form of its additional, invisible dimensions. Naturally, subsequent efforts by theorists were directed precisely at this. Initially, mathematically, only a few ways were found to correctly compactify the 6 dimensions. The simplest and most well-known of these was named Calabi-Yau space, after its discoverer and the person who proved the possibility of such a space existing. However, over time, virtually every month, new and diverse geometries emerged that eventually passed string theory's mathematical validation. Their number reached dozens, then surpassed hundreds, even thousands. Eventually, the number of ways to compactify extra dimensions exceeded 1 million, and by the mid-1990s, this figure had grown to a number for which no name had yet been coined. How then, from this immense diversity, could one select the single correct geometry to yield verifiable predictions? Naturally, the dream of experimental prediction quickly faded. Once again, string theory became a collection of mathematical formulas that could not be experimentally tested. Its popularity declined anew, as string theory's promises to society remained unfulfilled. However, as often happened with string theory, its theorists found a way to overcome this problem as well. At least, they attempted to. An intriguing proposal was put forth by Leonard Susskind, one of the pioneers of string theory and well known for his popular science lectures. Susskind suggested looking at the problem of dimensions from a radically different, cosmological angle. He argued that if mathematics doesn't point to one particular form for extra dimensions as the sole correct one, then perhaps there is no single, correct, form. Perhaps all of them are correct, but not for our universe, rather for a multitude of other universes, each with its own unique physical laws. Thus, Susskind proposes turning to the multiverse theory, which, in his view, gains a certain meaning when interpreted through the lens of string theory. In other universes, possessing different geometries for their extra dimensions, the modes of vibration would impart different properties to particles. For instance, in one such universe, an electron might be slightly heavier, or the nuclear force a bit weaker. This could render nuclear fusion impossible within stars, preventing them from igniting. There would be no heat, energy, or chemical conditions for life to emerge. Each of these universes would have its own distinct physical laws. Humanity exists only because, in our universe, the local laws of physics permit life to form. The features observed here would cease to be universal truths. Instead, they would merely be local laws dictated by the geometric form into which the dimensions of our universe are compactified. While this idea may sound somewhat grand, its scientific validity remains questionable. The multiverse is traditionally, to put it mildly, a subject of extensive debate, and its linkage with string theory appears to be a rather bold step. For proponents of the multiverse concept, such a connection, conversely, lends weight to string theory as a potential model of the universe. Skeptics, however, would likely assert that this is an absurdity that merely underscores the speculative nature of the theory itself. It should be noted that from the mid-1980s to the late 1990s, string theory underwent several revolutionary transformations, during which its leading theorists tirelessly refined its equations. It was discovered that the theory should include not 6, but 7 extra dimensions. In addition to strings, membrane-like objects called branes also emerged. Furthermore, it was established that the various versions of string theory, of which there are 5, are fundamentally identical. Consequently, it seemed logical to unify them into a single so-called M-theory, which physicists, incidentally, have not yet fully comprehended and are only beginning to uncover its properties. But one thing remains constant: the more fundamental problems string theorists solve, the more new concomitant complexities arise. Remarkably, despite all these difficulties, string theory maintains a certain popularity among young scientists willing to pursue it. Universities offer courses on string theory, and hundreds of scientific papers on the subject are published annually. This is undoubtedly explained by the absence of a more advanced alternative in the field of quantum gravity. It must not be forgotten that, unlike loop quantum gravity, strings integrate both the effects of quantum mechanics and general relativity, doing so in a highly aesthetic manner. In such cases, it is usually said that the theory possesses mathematical appeal. Critics, in turn, point out that mathematics also elegantly described the cosmic ether, but that concept ultimately proved to be erroneous. Among the well-known critics of string theory was Richard Feynman. He expressed his view on it as follows: "I don't like that they don't calculate anything. I don't like that they don't check their ideas. I don't like that for anything that disagrees with experiment, they cook up explanations, they make adjustments to say, well, it still could be true. For example, the theory requires 10 dimensions. Well, maybe there's a way to wrap up 6 dimensions. Yes, it's mathematically possible, but why not 7? Sheldon Glashow, another prominent physicist of the 20th century, remarked, "Superstring theorists have not yet proved that their theory actually works. They cannot demonstrate that the standard theory is a logical consequence of string theory. They cannot even be sure that their formalism includes a description of things like protons and electrons. And they have not yet made a single tiny experimental prediction. Worst of all, superstring theory is not a logical consequence of some appealing set of hypotheses about nature. You might ask, why do string theorists insist that space is nine-dimensional? Simply because string theory makes no sense in any other type of space. There are, incidentally, even more radical comments, literally calling string theory the worst event in the history of physics. The reason for this is not so much the theory's shortcomings or lack of experimental confirmation, but rather that a vast number of physicists have dedicated their careers to it, and continue to do so, yet after 50 years, not a single convincing result has been obtained. On the other hand, one cannot ignore the undeniable positive aspects. For example, the very history of the theory's development testifies to its potential reality. Theorists consistently uncover new features that, like puzzle pieces, fit together into a vivid logical picture. Furthermore, the development of the theory has simultaneously led to significant breakthroughs in mathematics, topology, and even computer technology. However, perhaps the most impressive achievement of string theory is its ability to synthesize Hawking radiation with the laws of information conservation. Of course, this is not yet a definitive model of black hole radiation, but at least it has made it clear that string theory has the potential to solve truly deep physical problems. In summary, one could say that if Hollywood were indeed to make a film about string theory, audiences would be in for a genuine drama. However, the ending of this drama remains unknown. It could be another inspiring story of humanity taking a huge leap in science, forming one grand theory of everything. Or, conversely, it could turn out to be something akin to a true tragedy, recounting the terrible misallocation of resources and entire careers of brilliant physicists who dedicated decades to an idea that proved to be an illusion. As is evident, the stakes are very high. For now, quantum gravity is still hidden from us beyond the event horizon of a black hole and beyond the inflationary expansion in the very first moment of the universe. However, as noted at the outset, in their attempts to find a unified theory, string theorists have advanced much further than all others. Thus, despite all the debates, doubts, and criticisms, string theory still manages to maintain its position as the leading mathematical model of the universe, potentially capable of unifying all of physics.